Day 2 of the Geophysics Marathon in San Francisco. Scientists streamed to and from hundreds of poster presentations and talks in the cavernous Moscone Convention Center. I caught up with another NASA new investigator whose research is near and dear to Californians. He showed me his talk here in Moscone Center South.
My name is Gareth Bunning, and I'm an assistant professor at the University of California, Riverside. My main field of research is into the movements of faults, either in earthquakes or slowly in a form of motion we call creep. A creep is a name we give to a behavior which has a movement which is slow and steady. So we could talk about soil creep, where slopes slowly move and things like that. But in terms of faults, we are talking about a movement of a fault which is slow and steady, and in the absence of large earthquakes. So normally what we expect to see on a fault is that you have two plates moving, or two blocks of the Earth's crust moving with respect to each other on a fault, and that fault most of the time is locked by friction as this movement is trying to occur. So the stresses that the two blocks impart on this fault do not exceed the friction that's holding the fault together, until suddenly it goes bang in one earthquake. In the case of a creeping fault, that doesn't happen. Whatever the frictional state of the fault is allows it to move very slowly without having any large earthquake. And that's really quite unusual. Most of the faults that have been observed in the world don't creep. This is a project that has been funded by NASA as the education outreach element of a new investigator grant. And the grant is to study fault creep in the San Francisco Bay Area, Northern California in general. But the Hayward Fault is currently considered the most dangerous fault in the Bay Area. In some way, if we know where the fault is creeping, we know where it's also not creeping. And it's the areas that are not creeping that are the ones that will have earthquakes. Here's some examples of creep damage to various things in northern and central California. So this is where the Hayward Fault goes through a wall.
So it actually broke that crack through that wall?
Yes, and the fact that the crack is diagonal is quite instructive. So we can say diagonal cracks can only be caused by shearing. So actually wrenching of the wall by lateral movement. So I've been making measurements from space for some time of the movements that these faults cause. So the technique I use in most of my research is a technique known as INSAR, which uses satellites that beam radar essentially to the ground. And they're in orbits which repeat every few weeks. In the case of this particular satellite, which is a European satellite known as EOS-2, that has a 5-week repeat, so every 35 days it passes over the same point. And it emits beams of radar in microwave wavelengths. The wavelength's about 6 centimeters. And it scatters off the ground and is returned to the satellite. What we measure is the amplitude and the phase of the return of the radar to the satellite. So the phase is essentially the number of wavelengths between the satellite and the ground. And if the ground should move, then that phase will change. Red colors indicate movement away from the satellite. The satellite is flying from north to south and it's looking down and to the west. So red movements are movements either down or to the west. Blue movements are the opposite, they're movements up or to the east. The project, I came up with the name Citizen Creep Meter. A creep meter is an instrument that is designed to measure creep on faults, and there are a few of them in the area, but they tend to be quite difficult to get permission to install, and so instead of using instruments, I thought I could use people. People are much more flexible. And the idea for the project was that wherever a creeping fault interacts with the built environment in one way or another, you'll have changes to those structures which are obvious and visible and should increase with the changes, the breaks, the offsets should increase with time. At the moment we have involved 2 local high schools in the project through this non-profit in Fremont. We have teachers that show up from those schools to our outreach presentations, and from there certain students then volunteered to take part. So this is one of our original photos from 2009 in one of the residential neighborhoods in the south of the city. You can see there's a small offset in the curb. And this is a photo taken 18 months later by one of our students. And well, if you look at the difference between the two, We haven't managed to completely co-register them, but you can see that there are some visually obvious changes in the curve. So a centimeter of movement actually is very consistent with the rate that we would expect to see. If a centimeter essentially means that we're getting, in 18 months, it's about 6 to 7 millimeters of movement per year, which is what we measured from satellite.